In order to understand EEG well, it is important to understand polarity rules. The basis of EEG recording is a differential amplifier, which detects signals from two inputs, shown here as input 1 and input 2, and gives an output as the difference between these two signals. Brainwaves recorded on EEG have amplitudes in the order of microvolts. What a differential amplifier allows us to do is filter out other ambient electromagnetic noise. If you can imagine two tracings which are almost identical except for one small difference, the difference in this case we could think of as the actual brainwave, while the other movement we can consider ambient electromagnetic noise. I will mark the difference in red so it is seen more easily. If we put these two tracings through the inputs of a differential amplifier, you see that everything in common is cancelled out, resulting in a flat line, while the difference, represented in red, remains. The quality of the amplifier, in other words, the ability that the common waveforms are cancelled out while differences remain, is known as the common mode rejection ratio. Modern amplifiers have extremely good common mode rejection ratios. One way to think about differential amplifiers is to think of the common game that is seen on children's menus at fast food restaurants everywhere. There are two pictures, and the child is asked to notice the difference between these two pictures. For those of you playing along at home, I have outlined the 6 differences between the two pictures using red circles. Let's extend the metaphor and call the first picture input 1 while the second picture is input 2. In this case, we input the two pictures through a differential amplifier. And if we look at the difference between these two pictures as an EEGer might, we see that the difference might look something like this. This metaphor is an important reminder that we are never dealing with absolutes with EEG, but only differences. Because we are dealing with only differences, by convention, any tracing on EEG is actually a relative tracing rather than an absolute, and represents the difference between two inputs. In this case, we will label them generically input 1 and input 2. The tracing is sometimes referred to as a channel. By convention, as in this case, if there is an upward deflection in the channel, we say that input 1 is negative with respect to input 2, or looked at another way, input 2 is positive with respect to input 1. Similarly, if we showed a slightly different tracing, this time with a downward deflection, we could say that input 1 is positive with respect to input 2, or input 2 is negative with respect to input 1. Students who are new to EEG sometimes find this difficult as, counterintuitively, an upward deflection is negative in the first input, while a downward deflection is positive in the first input. We can use the polarity rules to come to conclusions about abnormalities, such as in this example. A quick look at the EEG would identify an abnormality in the right temporal region here and here. Let's take a more careful look at this abnormality. The red line traces over the point of interest in the first channel. You can see that the sharpest waveform has a downward deflection in the FP2-F8 channel. Using our polarity rules, this would suggest that either FP2 is positive with respect to F8, or F8 is negative with respect to FP2. We'll have to look at more channels before we can come to any further conclusions. If we look at the next channel, which is F8-T8, we see a slight upward deflection at the sharpest point. We can say that this would suggest that either F8 is negative with respect to T8, or T8 is positive with respect to F8. What we see in common between these two tracings is that F8 is relatively negative in both channels. This gives us an idea that F8 is probably negative in an absolute sense. As you can see, this is where a downward deflection in the first channel changes to an upward deflection in the second channel. This is sometimes known as a phase reversal. This term is somewhat colloquial, but it is useful at identifying regions of maximal negativity. Therefore, we can conclude that the area of maximal negativity is at F8. In this case, this is a right anterior temporal spike. However, the idea of a phase reversal, while helpful, cannot always allow us to come to conclusions, and so we have to go back to the polarity rules. Let's look at another example. This is an example of a waveform that is often seen during sleep. If we just take a single one of these waveforms and look at it on both the left and the right side, again we can apply our polarity rules. But this time we will start from posterior to anterior. In the P701 channel there is an upward deflection. Using our polarity rules, this means that either P7 is negative with respect to O1, or O1 is positive with respect to P7. Let's look at the additional channels. We can see that actually at T7, P7, the line is relatively flat or isoelectric. By EEG convention, this suggests that T7 and P7 are the same. Further up, we see that all the other channels are flat as well, suggesting that all of these electrodes have similar or the same waveform. Therefore, the electrode that seems to have different activity is O1, and this suggests that we have a positivity at O1 or in the occipital region. If we do the same process on the other side, we see that O2 is positive as well. Therefore, we have a positive waveform in both occipital regions. This is actually a normal waveform that we'll talk about further in additional videos, called a positive occipital sharp transient of sleep, also known as a POSTS. It is important to have a good understanding of the polarity rules when we look at more complex examples, such as this one, or this one.